All right, 2002. Here's question 1, form B, whatever. Here we go. So let's get reading here. It says that R is the region bounded by the y-axis. That's this line right here, and I know you guys know that. And the graphs of that guy and that guy, we have. Man, look at this image. It's so nice. It gives it to you right there. That guy's what I'm talking about. I'm talking about this guy. Okay, so that curve is our lower curve for this region, and this curve is our upper curve. As shown in the figure above, actually it's to the right, but this is a release question, that's why it's on the right. Okay, find the area of R. Now, in order to find the area of R, what we're going to have to do is we're going to find the area underneath the upper curve, and then we're going to find the area underneath the lower curve and subtract them. And actually, I'm going to shortcut it and by combining them into one integral. So I'm going to go, here's my integral, combining them into one integral. I have the upper function, 4 minus 2x, and I'm going to subtract from that the bottom function, which is x to the third power plus over 1 plus x squared. So pretty, so nice. Alright, and then so now I need my lower and my upper bounds. Well, since this area is bounded by the y-axis, the lower bound is 0. This point right here where the two lines intersect, that's the end of region R. So what we need to do is we need to find the intersection between those 2 points. So we got to bust out our calculator. So we go to our calculator. I cleared it. Go to the y equals window. We'll plug in some functions there. Let's plug in our 2 functions. We have 4 minus 2x. That's one of them. So I'm going to put in 4 minus 2x. And then I'm going to go down to enter another one. The other one is, x to the third, raised to the third. I'm going to get out of the exponent, divided by, and I'm going to need parentheses on this one because there's addition. We have 1 plus x squared. Close the parenthesis. Cool. Now if I hit graph, I should be able to see what I see on the FRQ. Oh, it's so tiny. Let's zoom in just ever so slightly. Zoom in. Now this is just preference. You don't have to do this. Oh, that's nice. I like that. Okay, cool. Now there's now just to review, what we're trying to do is we're trying to find this upper bound. We're trying to find where these intersect. We have the lower bound, which is 0. We're down here. This is 0. Whoops. That's 0. But what is this one? What is that x value where they intersect? So what I need to do here is I'm going to use my calculator. There's 2 different types of functions or buttons that you're going to use to find functions. There's a math one, and there's this one up here that says calc. Whenever you're working with your graph right here, use the one that says calc. So I'm going to hit second and hit calc, and I want to find the point of intersection. So I'm going to hit number 5. Boom. And then the calculator is going to go through a process. It's going to ask you, what is your first curve? And then what is your second curve, and where do you want me to guess where they intersect? And so right now, I don't know where the thing is, but it says, hey, is your first curve this one? I'm going to say yes by hitting enter. And then it's going to say, hey, is your second curve this one? I'm going to say yes by hitting enter. And then it's going to say, okay, where do you want me to guess? And the reason why I asked that is because sometimes functions intersect at more than 1 point. And so you have to put your little star thing right here close to the point of intersection. Now, I'm pretty confident that there's not another point of intersection pretty close to this, so I could stop right here and just hit enter, and it'll find my point of intersection. So I'm going to stop right here, and then I'm going to hit enter, and it'll find my point of intersection. Boom. Okay, so now it has my star right on the point of intersection. 1.48766644 is my point of intersection. So if you guys look on your, don't look right now, but if you guys look at the answers that College Board usually releases, they will have 2 answers usually, and that's because they'll use this number for the upper bound, or they'll use a number rounded to the 3rd decimal place. But I always like to be super duper duper safe, and I always use the whole number. So 1.48766644. So I'm going to write that down. 1.4. Boom shakalaka. There it is. So I set it up. Yay. Now, since this is a calculator problem, let's just throw this bad boy inside of our calculator and get it done. And you know what's beautiful? Is that we already wrote these functions down once, and we stored them in the y variables, the y vars. See, check this out. If I go back to y equals, you see that right there? y1 equals that, y2 equals that. So when I say second and go back to, I hit quit, go back to home, and I want to find the integral that I just found, I'm going to hit Math and then 9, because that's the FNINT. That's the integral button. My lower bound is 0. My upper bound is 1 point, what was the rest of it? 4876644. 4, 8. Dang it, where's my point? Ah. This calculator like goes really slow. 1.4. Is it 1.1 or 1.4? 876644. Now check it out. I'm going to use my y vars. Here we go. We're going to say vars, then go to y vars, and say in the function window, I want y1, and then I'm going to go minus vars, go to my y vars, and then function, and then y2, boom shakalaka daka, and then I'm going to go over here and put an x right there. If you don't put an x right there, you'll get a syntax error. I hit enter, I get my answer. So beautiful. 3.215. I'm going to round that one. 3.215. 3.215. There's your answer. That's the area of the region R. Alright, the next question says, on letter B, find the volume of the solid generated when R is revolved about the x-axis. There's the x-axis. We're going to revolve that area, so we're going to have B. Alright, now, whenever you revolve an area around something, like, you see this area right here? When I revolve this, I'm actually there's going to be a hollowed out point when I revolve this. You see this part right here? This? I'm going to shade this in green. This will be hollowed out. Okay, so what we need to do, actually, the concept behind this is we're going to find the volume of the solid that this function forms, and then we're going to find the volume of the solid that this function forms, and then we're going to subtract the two volumes. But there's a simplified way to write this. Okay, I'll write it the long way, don't write it, and then I'll write it the shorter way. Here's the volume of the outer curve. So it's 4 negative 2x. So I have 4 minus 2x. That is the radius of my circles. You guys know how to find the area of a circle? See, if I rotate this, it would be like, wee, and then like behind it, you would see the dots because you can't really see the line because it's behind it. All right, so when you rotate this, this is your radius. That's a bad illustration, sorry. That distance from the x-axis up to the line, that's your radius. And this function right here will give you that distance. I want to talk about that for a second. I'm going to press pause on this. Let's talk about how this right here tells you the distance from the x-axis up to the line. If I had, let's say this x right here equals 1. I don't know if it does. I'm just going to pretend it does. So x equals 1 right there. If x equals 1 right here, and I plug it into this equation, what do I get? I plug in 1 right here. It's going to be 2 times 1, which is 2. And I subtract that from 4. What do I get? 2. So the distance from here to here, whoops, from here to here, from that point to that point, the distance is 2. Actually, that's not how you would write it, right? You go like this. And you say, oh, the distance is 2. So the distance is 2 right there. And that is the measure of the radius of that circle. Now, there's a bunch of these circles because we're trying to find that volume of this. So we got to find the area of every single circle. There's a circle there. There's a circle right here. When you rotate it around the x-axis, there's a bunch of circles. And so we're going to plug in all of the numbers from 0 all the way to 1.48766 or 6644. We're going to plug in all these numbers to these radiuses, and that'll give us the volume of the solid when you revolve 4 minus 2x around the x-axis. Put a dx right there. Boom. Done with that. Okay, well, what about the other one? The other one, the lower curve. The lower curve, we're going to have the same lower and upper bounds, 1.4876644. And my lower curve is x to the third power divided by 1 plus x to the second power, and dx. Square that, multiply it by pi. Same thing as what we just did, except this one finds the volume of a smaller shape formed by this little baby area right here. Let's shade in that little baby area so you know what I'm talking about. This area right here, when we revolve this around the x-axis, it's going to be a very small part of it. But This is not what the question is asking. The question is asking what's the volume of the solid when you rotate r around the x-axis. So you're going to have to take this bigger volume and subtract this smaller volume from it, so you can take this hollowed out part. Okay, and so you would just write minus. Now if you wrote it like this, it is correct. You're going to get the correct answer, but everything that I just did would take too long. You guys want the shortest possible way to do this. So check this out. Instead of writing two integrals, I'm just going to write one. I'm going to write 4 minus 2x, which is the radius of the outer circle, and then I'm going to subtract from that one the radius of the inner circle that says x to the third power minus 1 plus x squared. And I put dx right here. Okay, if you plug that into your calculator, boom, you got the answer. And you only have to do one integral for that. Let's go back to this. How would I find the distance of just between these two right here? Actually, that question, I don't think it's going to help us very much right now. Let's just go on to the next question. Let's plug this into our calculator. Okay, we got the integral. What's that?
Use that function.
Oh yeah, I could just go up there and copy that. But then I have to do the insert button. That's going to take me forever because this calculator is slow. So 1.487664. And then I have y1, so I'm going to go vars, y-vars, function, and I want y1, and I'm going to square that thing, and then I'm going to say minus, oh, I forgot the pi, huh? Oh, it's okay, I can multiply it by pi at the end. Vars, and then y-vars, function, I put the y2 in there, and I'm going to square that dude. Okay, so let's put our x in there. And then at the very end, since I didn't do it at the beginning, I'm going to do it at the end. I'm going to multiply this by pi to get my final answer. Boom. 31.884. Actually, let's just do 31.889. That sounds good. Did I round it wrong? 5. 31.885. I'm good at rounding. I teach calculus. Okay, let's do letter C. All right. The region R is the base of a solid. Ooh. For this solid, each cross-section perpendicular to the x-axis is a square. Oh, yeah. Remember that distance question I asked earlier? This is what's going to come in handy. Find the volume of the solid. Okay, let me clear out my picture here. All right, now this is huge right here. Perpendicular to the x-axis. Now, I don't know if you'll get a question where it says perpendicular to the y-axis, but if it does, you're going to need to make functions of y instead of functions of x. Because we're perpendicular to the x-axis, we need functions of x. So we have a function of x right there and a function of x right there. Fantastic. So in this region, we have squares. I'm only drawing 4 lines to represent 4 squares, but there's an infinite number of squares in this region. How come we could only see lines on this problem right here? So isn't this supposed to be a square? Because we're looking down on it? Yeah. This is really hard to draw. It's hard to see. Wow, that's a bad one. Okay, can you see the square? It's like popping off of this. We're kind of looking at it from the right side now. We kind of tilt it over. Now we see the square right here. We have to find the area of every one of these squares and add them together. That's how we're going to find the volume of this thing. So, how do we find the area of a square? We just take one side and we square it. No problem. So that's my S. We take one side and we square it. But how do we find the sides? Here's the side. How do we find the length of that side? Okay, let's go back to what I was talking about earlier. Let's pretend that this is a 1. Let's pretend that x equals 1 right there. I mean, there's a bunch of other x's that we can do, but 1 is very pretty and nice, and I want to try to help you guys understand this concept. If I plug 1 into this equation right here, I'm going to get 2. Right? This would be 2, and I subtract that from 4, that would be 2. So that means the distance from the x-axis all the way up to that line is 2. But I don't want that. I don't want that whole thing. I want just that. So how do I take off this little part right here? I'm going to have to find the distance from the x-axis up to that line. And this equation right here is going to give you that. So let's plug in 1 to this. What do you get when you plug 1 into that? Let's see, that would be 1 up top, and on the bottom you get 1 plus 1, so it's 1/2. So we get 1/2. So if that's 1/2, if this whole thing right here is 1, but in this little or this whole thing is 2, and that little part right there is 1/2, what is the distance of just this line? The distance of that line would be 1.5, because you would go 2 minus the 1/2, right? Right. So if we ever wanted to find the distance between two numbers, you just have to take the bigger number and subtract the smaller number. You'd find the distance between those two. So what we're going to do right here is we're going to take the upper function and subtract the lower function, and we're going to plug in all the x values like we did right there with the 1. We're going to plug in all the x values from 0 all the way to 1.48766644. Let's do that. 0, 1.4876644, and I'm going to have my top function, 4 minus 2x, and I'm going to subtract from that my bottom function, which is x to the third divided by 1 plus x squared. Oh, so nice, so pretty. And then dx. Okay, but this is not my final answer, because all this is going to do is this is going to find the length of every single one of the sides of these squares inside of here, and it's going to add them together. But that's not what I want. I don't want to add the lengths of the sides. What do I have to do with all these? I have to square all these sides. So I'm going to put brackets around this and put a little 2 right there, and boom, we got our volume. Let's see what that looks like on our calculator. Alright, I'm going to try this. Sometimes this takes too long though. We're going to take that, and I'm just going to hit enter, and it's going to redo it for me. Do I want that pi there anymore? Nah, I don't need that pi. I'm going to delete that. That's not a delete button. Go back. Dang it. Now I'm way over there. Okay, well, I'll delete that at the end. Okay, first I gotta... Oh, man, this is ridiculous. I want to put a parenthesis right here, so I'm going to say insert. That's not insert. Oh, man, I can't... This is making me so frustrating. Alright, let's try that again. Second, insert. And I'm going to put a parenthesis right there, because I got to square this thing, right? And I got to get rid of those squares right there. So let's delete that. Delete. Delete. And I got to delete this other squared right here. Squared. Delete. And delete. And let's put a close parenthesis there and square that whole thing. Alright, cool. That's what we have right here, right? We have this function minus this function, and we square it. Right? Okay, so now I got to take off that pi. Alright, let's take out that pi. Good looking out, guys. You guys are making sure I didn't do it. Okay, boom. 8.997 is the volume. Beautiful. Oh, it took forever.